down to you in the corner. The episode number 38. What happens when you radially pull a piezo crystal ring? Now, I'll start this discussion by talking about pulling in general. So, what is pulling? After you create your piezo ceramic, which is also has to be ferroelectric for the pulling process, but that's usually a given for the most cases. We have to apply large voltage, and that creates an electric field going from positive to negative side, and that also then orients your polarization direction in the same direction as your electric field. So pulling orients your polarization, creates a net polarization in your device or your material, which then allows your piezo ceramic to have your ferroelectric piezo ceramic, like PZT, to have net piezo properties. You can also do something else. You don't have to only pull around the thickness, you can pull in different directions. So for example, if we pull along the width or the length here, then we apply a voltage on the top and bottom of your piezo instead of creating a long, instead of modifying your dipoles to be larger or smaller. That's a longitudinal piezo effect. You actually can if you apply voltage after pulling in the length, if you apply voltage on the top and bottom, you'll then cause transformation. You'll cause rotation, which is shear. Radial pulling. This is cool, interesting. It can be difficult because the radial thicknesses are much larger thicknesses than you typically will have in your ultrasonic typical crystals. So you have a very large thickness, you may not be able to pull completely. So that is one question, whether you can properly pull these ceramics or not. But assuming you can pull them, what then happens? You have to, so you apply an electrode on the inside and an electrode on the outside, and then you provide that same voltage, and you get radial pulling. So let's say this is the ring, and you have your positive in the middle, the negative on the outside. The electric fields will radiate outwards from positive to negative, and there'll be a higher concentration of field in the center and a lower concentration on the outside. Now, this is not true for uniformly pulled devices where you're not pulling on a curved surface. At least a curved surface with negligible thickness. The thickness is not negligible. The curvatures, the ratio between surface areas are not similar in these two cases. So we're talking about that kind of radial pulling, not where you have a very thin ring. It's not going to be a problem. But if you have a thicker ring, like what's traditionally used for power or ultrasonics, then you're going to have issues with pulling. Stronger fields in the center, less stronger fields on the outside. Therefore, you have higher piezo properties in the center and lower properties on the outside. So that's represented by the dark green color, darker green shade. The lighter green shade is lower pulling. So that would obviously cause non-uniformity when you apply voltage. Cylinder-looking things, but imagine it goes all the way outside the paper or outside the screen and goes all the way around. If you applied a positive voltage in the center and negative voltage on the outside, you are putting an electric field in the same direction as the polarization direction that we did. Assuming you put a positive in the center for polarization. Therefore, you have extension in that direction. It's almost like the D33 effect, except radially. But note that it will be harder for the center part to move because of the stiffness it has to oppose in the center. They're stiffer, rings are stiffer in the center, and less stiff on the outside. There's less material to push aside and pull away from. Anywho, you'll have the length extension, so the disc will expand outward. And it'll also get skinnier in the same result. And I did this exaggeration such that you may have different extensions depending on your degree of pulling that you have. But you'll basically have a D33 effect or a D31 effect, except not in that case, except with the different pulling. So you would expect such a resonator like this to have a higher coupling factor and the radial resonant mode than the radial mode of a thickness pulled, because you're exciting now in the effective thickness or the effective polarity, because the resonance mode is exactly aligned with the polarization directions. You'll have higher coupling, but that obviously comes at a huge cost of can you even make the thing, and even if you can make it, you'll have natural property variability, which is going to create a huge mess. So let's just see here. Say here. So we radial pulled. No, what's that for? All right. So we have a radial pulled. We chopped in half. Now let's say we operate this in shear. We apply a positive and negative voltage. We have orientation of the dipole as seen here. That's going to cause this effect, where you have this disc which is kind of bending inward and outward. Let me do a little something for you. It's like this. So you have that disc kind of like this is more like it. All right. Imagine this is the outward face of the crystal. Yeah, a lot of back. So what applications can be used here? For the bolt Langevin transducer, no, it's not going to work very well at all. Although, because it's used in the thickness mode anyway, so why would you radial pull something that's normally a thickness mode? It doesn't make sense to me at all. So you don't use it for clamped Langevin transducers, bolt clamp transducers. Maybe for some specific applications that could be useful, for example, energy harvesting, or applications where you specifically need something radial, but and it's normally operated in the D31 type of mode. So it's normally radial, it's operated in the D31 type of mode, and you want to improve performance. In that case, for example, for a symbol transducer where you have two metal end caps, and you also have, let's say, a disc in the center. Radial devices just work better in general. You want to have symmetry. It helps a lot. Besides having square transducers whenever possible. So in this case, if you squeezed on it and you measure the voltage on the internal and external areas, you would have a very high voltage developed due to the larger thickness and the radial pulling. So it could be used in some specific applications, but I think it's more of a novelty and something interesting for researchers at this point. I'm not sure if there's a specific application for radially pulled devices. There are cylinders, piezo cylinders, which are radially pulled effectively, but because of the thickness it doesn't vary too much. They don't provide as odd of a situation as does a thicker or radially pulled ring. So thanks for watching. This is Dr. Shikani from the Piezo SHOCK Show. Please look in the description for links to the presentation notes. Also, a link to sign up for emails. Whenever one of these videos comes out, you'll get an email with a description of the video, as well as the presentation notes that will entice you perhaps to look further and watch the video itself. All right, thanks for watching. See you next time.